My talk is on a fresh look at evaporation in the ocean, and being faithful to my approach that we should think lagrangianly and compute perhaps Eulerianly. I'll take a Lagrangian approach to the evaporation process, and I'll show you in a minute what it means. And this is a paper that was published last year. Here are my collaborators on this work. And towards the end, I'll tell you some new thoughts about what elapsed since then. So the outline of my talk will be, I'll sketch very briefly the classical, traditional approach in studying evaporation in the ocean. It's not that much. And then I'll tell you a little bit about how a Lagrangian view can change things and perhaps make it more generally applicable. And then I'll show to you that the simple proof of concept does work. And then towards the end, I'll show you how I think you can put it to work and learn something new about little things that we thought we knew, but we really didn't know that well. So what do we know about evaporation? Usually we look at the Eulerian approach, in which we look at the net evaporation. When I say evaporation, I mean net, the excess of removal of H2O molecules compared to what comes in. So it's the excess of evaporation over precipitation. And usually, traditionally, it has been done in a closed basin. So you should think about a lake. Where's the Hungarian lake, which I forgot its name? A lake or Mediterranean or Gulf of Eilat or the Red Sea, a closed basin. And in the basin, you'll see in a minute that the net evaporation, what comes in and out of the basin, is closely related to the flux of water coming in from the adjacent, say, ocean. So in the case of the Mediterranean, you should think about the Atlantic. In the case of the Red Sea, you should think about the Indian Ocean, and so on. So as you see in a minute, the two go hand in hand, the net evaporation and advection. And in semi-enclosed basin, like the simple examples I'll show in the next slide, we well know Knutson. Am I pronouncing it correctly, Knutson? Yeah, the K is pronounced, right? Even though it's K in the, okay. Just making sure that I'm not pronouncing it incorrectly. So the Knutson relation gives you a very simple relationship between the net evaporation. Okay, this is taken from the textbook by Knutson on physical oceanography. And I was one of his last TAs before he became the assistant to the Secretary of Commerce in the US government and drove limos and all that. In his book, what you can see is that if you have a net evaporation of magnitude of Q, say tons of water per year, then the conservation of mass of water in that basin maintains that the transport of water coming in and the transport of water coming out, which is both T out and Q, should equal each other, so the level remains constant. So that's the conservation of water, either mass or volume, if you want. It's the same thing. And the conservation of mass of salt gives you another conservation. In other words, the salinity, the amount of salt coming in, so the salinity times the transport of water coming in should equal the transport of, again, in kilograms or tons of salt coming out. So this is the conservation of salt. If you know Q, these two simple linear equations can be easily solved. And the solutions are known as Knutson relation. The outgoing salinity, the outgoing transport of water is equal to the salinity of the incoming water divided by delta S, where delta S is the difference between the incoming and outgoing salinities. And therefore, usually in most of the world ocean, these are about 35, not exactly. And this is very small, maybe 1 or 2 in PPT. So this is a large number. So there's a small engine in there, the net evaporation, that drives a huge transport of water in and out just to maintain, to conserve both the mass of water and the mass of salt that go in and out. So this is well-known textbook. I mean, don't need me for that. You have to know Q, and Q, the amount of water comes out. It controls large fluxes of in and out, coming in, water that come in and out. Now, if you want to know Q, there is really not such a good way of estimating it. And it's really frustrating. The reason is because evaporation is the main source of transfer of heat from the surface of the planet, the surface of the ocean or the land, to the atmosphere. So actually we think we cool off by radiation. No, we're warmed up by radiation, but the surface of the Earth, the main ingredient in the cooling of the surface is the evaporation, okay, the latent heat flux. And in a minute you'll see why. It's a huge amount of heat that goes in there. So if you just look at the experiment, say, we all can just take a dishpan, put it on the shore, and then you measure. It turns out that in dishpan experiments of evaporation, you get numbers that are way, way, way too high. And the reasons are because a dishpan doesn't usually create its own climate, whereas an ocean does. And therefore, what you see is the evaporation from land and not the evaporation from ocean. So dishpan experiments give you a very poor idea about what goes on in the ocean. It gives you an okay idea about what land, but this is not our focus here. So we don't know Q very well, and as you'll see in a minute, Q, the amount of water coming out, has to be estimated from a very complex balance of energy, of heat. And if you look at the balance of various terms, then it's obvious. The left-hand side is the amount of heat that goes into the water column in the ocean. Okay, so you have, think about the summer, so the water heats up. You can calculate the temperature and multiply it by the heat capacity, and then get the amount of heat that went into. And this heat that went into the ocean, if it's not zero, like if you think about 30-year averages, then of course it is zero. But if you think about this certain period, it's not. Then it equals to the balance of all these forces, the incoming solar radiation, for which we have a fairly good idea without cloud cover what it is, the net long-wave radiation that goes between the ocean and the atmosphere, and then the atmosphere back to the ocean. So it's a delicate balance, but somehow it's radiation, so we can control it. Then there is the evaporation, which is the largest component. And then there is the sensible heat flux. In other words, if the two temperatures are slightly different, then there is a transfer of heat from the warm body to the cold body. This is usually smaller. And then there is the advection of heat, which turns out to be very important, at least in some cases, at least in some part of the... So you have a very complicated balance of sources and sinks of heat, even if this is zero, even if you take the net heating of the water column to be zero. And while these are radiation, these two are hard to quantify. These two, I mean the evaporation, the latent heat flux, and the advected heat by the incoming water. So just a closer look at these two. We usually, when we want to do a heat budget in anywhere, we usually need to know these parameters, but we don't really know them. So we infer them from atmospheric measurements, such as the winds, which control the amount of removal of moist from the atmosphere, air temperature, relative humidity in the temperature in the atmosphere, cloud cover, which it's a lot of meteorological components we need to know in order to apply this balance, the aforementioned balance. And water temperature and the incoming water, of course, we can, this is hardly very poorly known. Now, all climate models, or even non-climate but weather models, of course, deal with this climate, and they use engineering tools, what's called the bulk formulae, because they have something that works okay, not based on very deep physics, and it gives us the result we want, and we're happy with it, at least to the extent that we need it for practical usage. But they give a very crude estimate, and one of the reasons is because while these two can somehow be measured at any location, if you really want to know them, the total heat that went into the ocean, the solar radiation, and the back infrared radiation, the other two are very poorly determined. And one of the reasons is that if you have removal of Q amount of water out, in grams of water, each gram of water, when it evaporates, takes 600 calories. In other words, it's equivalent to about warming a gram of water by 600 degrees centigrade. So it's the amount of heat that goes into evaporation is tremendous compared to the amount of heat that goes into warming by a degree Celsius or 2. So any error here in the amount of water evaporation leads to tremendous errors in the what we really want, which is, say, QT. So the advected heat and the evaporative heat go hand in hand in the sense that it's very hard to measure them, even with a bulk formula. So what am I suggesting? Of course, I'm not going to solve everything in one lecture, but let's try and make a progress. And the idea is that we sort of ignore the ocean when you come to ask about how much water evaporates from it and how much water is advected. We somehow look for the meteorologists to come to our aid, we the oceanographers, okay? So we, the meteorologists, come to help the oceanographers because the ocean just sits there, huge body of huge mass, and says, I don't know what's going on, you tell me what's going on. So let's try and see what we can decipher from the ocean itself. And the idea is, the idea I'll present to you is that we'll think Lagrangianly, okay? So we'll think about a column of water that moves in the ocean. Why it moves, I don't care. We don't care. It can move because of thermohaline, because it's part of the Gulf Stream. I don't care. As long as it moves in the ocean, at the surface of the ocean, subject to net evaporation. Okay, you can think about evaporation only, but if there is some fresh water coming in, I'm talking about the net. And as I said, I don't care why it's moving as long as it's moving. And I'll relate changes to water properties along this transect, I'm following the water column, to the net evaporation. And this is going to be not such a terrible task. Okay, so here's the idea. Okay, I have a column of water that goes a certain amount, distance x, while being subject to net evaporation. Now, the net evaporation, of course, removes a certain amount of volume from the column, and therefore the column should shrink, and we can calculate it. So we started with a height of h0, or volume of h0 times 1 meter squared, if we take a unit area. Then, after a distance x, if it moves with an average velocity u, and there is a certain amount of evaporation goes on the q, little q here, then a certain amount of volume is lost. And the way to relate it is by the continuity, of course. It's don't have to be a genius, very simple. The math is, by the way, you can relax. Okay, there are no differential operators, and it's manageable for everyone, even geographers. Okay, so the removal of height of mass of water at a certain amount is, of course, controlled by the net evaporation. So the h dt, delta h delta t, is equal to q. And the question is, how do we estimate t? So the easiest way to estimate delta t here, say, it's being advected, right? And if it's advected at distance x with velocity u, then the time is just x over u. So this delta h is just q times x over u. That's it. There isn't much to say about it. So I have an expression for delta H, and if I want now to think about the relative change in the height or the removal of mass of water, then I take delta H over H0, which I will call G of X. You'll see in a minute why I give it a certain name. And it's given by this formula, okay? And since this has dimensions of length, then this must have dimensions of 1 over length, so we'll call it 1 over L, where L is what I call evaporation length in a minute, and this is going to be U times H. Remember, U times H is the transport per unit width of the water going in that direction, in direction X, divided by Q, which is the evaporation rate, okay, net evaporation rate. Okay, so L gives me that sort relationship, if you will, between the volume per unit width that goes in that direction and the amount of evaporation, net evaporation, that the water column is undergoing on its way, en route. Are we all set on what I said? I mean, you're smiling, you're not crying, and okay, great, okay. Okay, so just to repeat what I said, this is what I said, and of course, if you want to think about what L means, this evaporation length, it means the distance that a column has to travel given this Q and net evaporation and velocity before it completely evaporates. In other words, where H at location X is equal to 0, or delta H is equal to H, or no water left. But you can also think about this function G, okay, as the ratio between two times. You can think about it as the X over U divided by H over Q, which is the advective time of advection, divided by the evaporative time, the time it takes to evaporate the column of water. Whichever way you look at it, okay, this G or this L, they are very intuitive once you think about what happens, okay? You go, you evaporate. Now, I should say that, so that's it. The model is done, okay? There's nothing more to say. I'll just do a little more balances of salt and things like that. But what I want to say is that in practice, we do not detect changes in height. So the height itself is being compensated for, stand here, that's it. Compensated for by things like entrainment, or, you know, there is no real slope of the water as you go downstream. There is something compensates for it. However, if you think about observable quantities such as the salinity, then these will be affected by the removal of water molecules only by the process of evaporation. So if we think about the conservation of mass of salt, then the salinity at point X times the height at point X should be constant at anywhere, irrespective of, because we have not removed any salinity, any salt molecule. And therefore, what you get from it, missed a little bit, is that the salinity at distance X over the salinity at X equals 0 happens to be just 1 over 1 minus G, just work out the algebra. And if G is small enough, then you can expand it to first order and get 1 plus G. The same G that we had when we had the mass of water. And there is the first limitation of this theory. It will work only if G, which is X over L, is sufficiently small for this first order expansion to be valid. As you'll see, this is not a big problem. It's true everywhere. But on the other hand, X to be large enough for the salinity changes to be detectable. If it's, if you go 1 kilometer, you won't see any difference, so there's no signal. So there is a balance between, on the one hand, making it sufficiently large for the salinity changes to be observable, and on the other hand, to be sufficiently small for this first order expansion to be valid. I just want to say 2 slides, and hopefully less than 1 minute, on the fact that salinity is not the only player. I'm not a geochemist, but some of my co-authors are. And with them, we worked out a very similar approach to the conservation of other conserved quantities, not heat or salt, because heat is not conserved, and salinity we already took care of, but for example, stable isotopes. Okay, now stable isotopes is a very strange field for mathematicians or physicists, and it's usually something, it's almost like a plague, let's keep away from it. But bear with me for, a minute or so. So the excess of, say, if you take the oxygen isotopes of O18, then it's usually measured in deltas, which is the delta is the ratio of O18 to O16, the rare to abundant isotope, compared to some standard which geochemists know what it is. It's small, or they change it every decade or so, what exactly is the standard. But for us, there is somewhere, maybe in Copenhagen, who knows where, a standard of water with known excess of delta O18, and everything is compared to that, and it's reproduced in other labs in the world. Not mine, though. And therefore, it's measured in excess of delta O18 compared to this standard. Now, if you look at the evaporation, in the process of evaporation, for reasons which are not entirely clear to me, but this was a major revelation in the second half of the 20th century, the process of evaporation is not uniform with respect to all isotopes of oxygen. Okay, so O18 versus O16, the ratio changes when you evaporate the water. For our purposes, all I have to say is that if you look at the water, not at the water vapor, not what goes into the atmosphere, then what happens is you can write it, the change in the relative composition of O18 as what you had in the beginning, times epsilon times ln F. F is what we would call delta H over H, the amount of water that remains, or 1 minus what you removed from what you had at 0. And epsilon is a known, not they debated, the geochemists, but is what's called the enrichment factor, which is related to the fractionation factor alpha. You open thick books like CRCs and you get the number from there, and that's what we go by, okay? So, those thick books of geochemistry and physics, constant, and all that. So you have the epsilon for delta O18. So the number F is just Hx over H0, which is 1 minus our G. So we can plug it in there, and lo and behold, what we have is that delta O18 at X is related to what happens in the beginning by exactly this function, okay? So the reason is that the Taylor series expansion, the ln function, is exactly linear with X as we expect, as was the case in the case of salinity. And by the way, you can do the same thing with deuterium if you have a lab that can measure it for you, but I'll show you in a minute. And therefore, you have deuterium and H1 are also related with the same relationship, only different values of this enrichment factor, etc. So to first order, all I'm saying is that this G, okay, that we computed before, is also determines the changes in the isotopic composition of the water as it undergoes net evaporation along X. If you haven't understood much of what I said about isotopes, you don't have to. Just remember that the changes are linear in X. Okay. So it seems like, on the blackboard it works well, but does it work in the ocean? I mean, how well does it work? Is it really something that we can apply? And the answer is, despite its simplicity, the answer is yes. And we took in this paper 4 very different oceanic circumstances or scenarios. One of them was the Red Sea, including the Gulf of Eilat here, the northern tip, for which we had cruise data from 2014. And we wanted to analyze both the geoisotopes and the salinity changes. We took the entire Mediterranean Ocean, averaging everything across the track from Gibraltar to Israel. This is Israel. We took another transect in the Indian Ocean for which we found both salinity and delta O18 data along this transect, 57, what is it, west, east, 57 east, I think. And the other extreme occasion is the Gulf Stream, which we said, let's try it. Okay, so you have very dry, slow-moving, almost nothing is moving, and very fast and hardly any changes in salinity in the Gulf Stream, and anything in between, variations in huge meridional domain and transect like this, and said, let's put it to the grinding machine, see how it works. Okay, and we had two sources of data. The first one was soda. It's not a drink. It's simple ocean data assimilation. Why did they choose this name? I don't know. Do you know? Soda. Anyhow, but it gives you what in meteorology you have those ERA, interim, and ECMW, all those repositories of data. SODA is one of equivalent oceanographic. And it gives you the data like almost anything you want in half a degree longitude and latitude. And it took 4 transects, and we averaged in the north-south in the Mediterranean, east-west in the Red Sea, and in the Gulf Stream we took all points in which the velocity was greater than 40 centimeters per second. So, you know, the heart or the core of the Gulf Stream, not worry about the surroundings. Okay, and we also had 2 cruises. We wanted to compare it to cruise data, not averages over 30 or 50 years, including models, but real data that was taken by good scientists, hopefully good, I don't know. We'll see in a minute if it's that good. And compare all of it. And in the Red Sea, we had data that both salinity, delta O18, and delta D that was given in that, was taken in that cruise. And in the Indian Ocean, we had salinity and delta O18 only reported here. And again, the data itself was uploaded and we could download it. And then we said, okay, let's go with that and put it in our simple model and see how it works. So this is how it works with soda. This is the Red Sea, Mediterranean. This is the Indian Ocean, and this is the Gulf Stream. 4 cases. And what you see here is that, number 1, the linear approximation, okay, of S as a function of X. Remember, in our theory, the changes in S had to be linear in order for the equation to apply. And what you see here is that the linear fit has a predictive value or correlation factor of about 0.9 something. In the Mediterranean, we have to apologize with the R squared being only 0.8. If you chop off the western part, then you get much more than 8, but I don't think we should cherry pick the data. So we just took across the entire Mediterranean. If you take a look at the Gulf Stream, which is very interesting, even though the range of salinity changes is very small, notice here we have something like 0.15 ppt, because it's very fast and there is no great changes in salinity. The linear fit is very good. It's about 0.9. And in the Indian Ocean, it's also very good because it's part of a very slow-moving gyre. So we have S of X that has a very good first approximation as a linear function. Now we can go ahead and look at what happens with the slope is 1 over L. And now we have the values of L. Let me just go, okay, from these linear slopes, I just put them all together here. So this is the Gulf Stream, very slow. Yeah.
So you're going, so on each of these transects, you're going radially. Is that right?
From where?
North to south, for example.
In the Gulf Stream, we went south-north. In the Indian Ocean, we went north-south. In the Red Sea, we went south-north, and in the Mediterranean, east-west. Okay, we averaged over the entire width of the Mediterranean, which can be 2,000 kilometers. But we average all the points, and that's why they call it.
If you had gone, for instance, if you had gone east-west in the Indian Ocean, you would.
No. We went along 57.
But I'm just saying the displacement, the direction will matter, right?
Right. But you'll get it in opposite sign. That's all you'll get, and we can handle it.
You might not get much of anything at all, right? You might get zero.
Right. All right. If you have to choose the transect. Okay. So cruise data. Okay. We wanted to compare to see if it works as well. Okay. So in the cruise data, here is the Red Sea. This is the data that was taken in that 2014 paper, which is based on about 2009, I think, cruise that was taken to the Seychelles. And as you see, once again, the salinity is very high correlation. There is no stable isotope repository of data. You just have to take what you can put your hand on. And the delta O18 happens to be with very high correlation, and so is the delta D along this Red Sea cruise. Linear fit, that's very nice, and lots of points. And again, so the linear fit means that we can put our model to work. In the Indian Ocean, there's a slight problem. I'll show you the data, but remember, it's heavily tilted towards a single point here. There's nothing I can do about it. It's 2007. I cannot go back and redo the analysis. But the linear fit works well in both cases. So even though it works well, it's, I'm not picking the data, but there is a very heavy reliance on one point. So what can we say about L? Here's a summary. Let's look at this column first, because this comes from soda. So what you see is sort of what you can expect. In other words, in the Red Sea, which is very dry and very slow moving, it's not, a fantastic current, you have an evaporation length, remember it's a length, that's 26,000 kilometers. So you have to travel, the water column has to travel 26,000 kilometers. This is 10 to the 6 meters or 10 to the 3 kilometers before you completely evaporate the top water. In the Mediterranean and in the Indian Ocean, it's not as dry and probably not as fast moving, so you need to go about, 85,000 kilometers. The Gulf Stream, on the other hand, is very fast moving and probably not such huge evaporation rate, so you have to go 500,000 kilometers before you evaporate everything. So number one, it makes sense. Number two, the error bars are not huge. A few percent will give you, but it's not as if we err by 50%. So this is insofar as soda. So you can now go to any place in the ocean, take soda, and calculate the evaporation rate. I'm not exactly sure why you'll do it. I'll tell you in a minute what I think you can do with it, but let's just work out the proof of concept first. So if you go now to the salinity in the cruises, then you see that in the two cruises, that what you see from the salinity is not that far off from the soda. In other words, 74, plus minus 13, it doesn't work out too badly with respect to soda. So I guess the implication is that we know how to measure salinity. In other words, the CTDs and development of automatic ways of measuring salinity work out pretty well in the ocean. Now, if you go to the delta O18 and delta D data, so I think it really speaks for how well you can measure it. So in the case of the Red Sea, we get similar numbers, and not, overwhelmingly different. Here we get somewhat different number by a factor of 2 in the case of the Indian Ocean and the delta O18. So by and large, except for this point, okay, it seems to work. Again, not so much different, but not exactly the same. And as I said, L is very short in the hot, dry, and slowly moving Red Sea, and very long in the fast and not so dry Gulf Stream, and somewhere in between in the Mediterranean and the Red Sea, despite all the inaccuracies. Okay, so the question is now, so what should we do with it? So there is a new tool in the neighborhood,
And how should we use it? What exactly should we do it for? So what I suggest is we now, remember, this was the definition of L. Let's now reverse it a little bit and write it as this way. So remember, now I have, this is the transport in the surface layer of the ocean. And this L I know because someone gave me good salinity data, or delta O18 data, whichever data you have. So now I have a direct link between Q and the surface transport, right? So having gone through hoops of Lagrangian model, et cetera, I now have an independent measure, not complete heat budget in the ocean where I have to know, or in a basin, where I have to know both the incoming solar radiation and outgoing radiation, et cetera, and sensible heat flux, and et cetera, just direct measurement of the ratio between the transport of water and the evaporation rate based on this evaporation length. Okay, so just to be on the same page, the values of Q, the rate of net evaporation, in many parts in the middle latitudes, okay, as you see, it works also very well in the equator, but Q doesn't vary tremendously. As I told you in the first slide, in order to change Q, you need to put in a lot of energy. To increase the net evaporation, you need to put in a lot of energy. And you can't really play with the energy that much. You can't make it twice as much. You can't evaporate 3 meters of water instead of 1.5 because you need a huge amount of heat, energy. Someone, another sun has to be out there to help you evaporate that much. But it can vary, maybe 10%, I don't know, between 1.5 meters per year and 2 meters per year, right? Is it a reasonable, a sensible number? What do you mean you don't know? You're an oceanographer. But it's, there are very few places where you have less than 150 and very few places where you have more than 2 meters per year. L, as I showed you, if you have good data, L can be estimated to about, again, 10%. Okay, I'll give you, if you want some more, it doesn't cost me anything. You can take 15% if you want. So we know the left-hand side to an accuracy of something like, 10, 20%. On the right-hand side, we don't have a clue. In other words, if you go to observations, so you have to first define what exactly is the height at which this transport is going. It's not so clear. What is the mixed layer, the permanent, the local? In some very special cases, you can perhaps detect or assign a value to this age, but it's not easy. And you, in many, many cases, suffers from errors that are hundreds of percent. We don't know whether it's 0 or 5 or 0 or 2 in many parts of the ocean. So while the left-hand side is known to within 10, 20, 25% or so, the right-hand side, up until now, if you go to soda, you can't really tell what it is. Okay, so let me show you, as I said, we should learn something from this tool, okay? So I started by looking at the equatorial oceans, I should say. So you have the Indian, Atlantic, and Pacific Oceans, and we just took east to west transects along the equator. Along meaning I think we took it, what I'm showing here is from 4 south to 4 north. We did the same thing with 2 south to 2 north. It's the same results. Okay, so what you see here is the salinity. Now, in all cases, you see that the best fit, linear fit, doesn't do a tremendous job, but it's not so bad, okay? 0.9 is a good number. Not so bad for geophysics data. As I said, it's westward, so we're going from east to west. And as you see, the salinity is increasing. Again, this is soda data. It's a global repository. And what you see is that if you look at the same data repository, the soda, and look for U and H, try to estimate it in any way, shape, or form. Take the temperature profile and average it over many seasons, etc., and try to calculate the depth of the mixed layer. You can't get a good handle of what H is, and U gives you literally crap because you don't even know whether it's different significantly from 0. But we certainly have here a slope, linear slope, that resembles what we see. So if you work out the machinery that I showed you before, it turns out that in the Pacific, the evaporation length is about, this is kilometers, so I changed from the previous slide, is about twice as large as in the Pacific and in the Indian Oceans. These two are about 160 plus minus 10%, and this is about 320 plus minus, I don't know, a few percent. So why, first of all, why is there a westward flow? If you take out all descriptive physical oceanography textbooks, the recent one is by Lynn Talley, you spent a sabbatical there, no? Which is an excellent textbook. I don't know how many oceanographers there are here in the crowd, but it's one of the best textbooks, and it's a remake of the very outdated descriptive physical oceanography textbook we had in last century. And if you read her accounts, it's not her, it's theirs actually account, they say, oh, you know why there is a westward flow in the equatorial ocean? It's very simple. We all know that there are trade winds in the atmosphere. It's got the convergence of the south and north flowing air masses that complete the Hadley cell, the surface branch of the Hadley cell. They converge on the equator and therefore generate a westward directed wind stress over the ocean. There is no Coriolis because F is 0 on the equator. So F is 0, no Coriolis, there is wind stress, so it pushes the water westward. That's why we have westward flow on the equator. Okay, it sounds reasonable. I'll tell you in a minute what, yeah, you want to ask something? No, okay. Feel free to ask because, you know, I'm about to finish in about 10 minutes, so I'll have time. So let's examine it. So why will the Pacific be twice? If you check the wind stress in the three oceans, it's the same. So if you have just force applied by this winds to the ocean, it's the same force. Why will there be twice as much transport in the Pacific Ocean? Okay, so if you look at the average Q, the rate of evaporation, no significant difference between the three oceans. But higher L, if we have higher evaporation, it means that there is higher UH, so there is a higher transport. It's for the same Q. Remember, L times Q is U times H. So same Q, twice as large L, twice as large transport. So intensity of wind is the same. Rate of evaporation is, again, the same to within, I don't know, 10%. What's the difference between the Pacific and the Indian and Atlantic Oceans? The only difference is the size. We know that the Pacific covers about twice as large zonal extent compared to the Atlantic and Indian Oceans. But how does the size enter the issue of wind-driven fluxes? So what I'm trying to propose is that if you stick to the wind-driven westward flow on the equator, you can't explain the observation of twice as large evaporation length. However, if you're an old-timer like myself, and you know that Henry Stommel lived in the last century and had unbelievable impact on, you're still alive when you were a student there, right? Yeah, you knew. Had a tremendous impact on physical oceanography in his fresh thinking and ability to take an thought experiment that seems completely out of contact with what we want to sense. Yeah, because it works here like this, it should work in the ocean like this. It's huge leaps of knowledge and understanding. So he came up in a very seminal paper that left its mark on physical oceanography in 1948 in his first explanation of why there is a Gulf Stream and Kuroshio and Brazil current, westward currents in the world oceans. And he proposed that there are gyres. I'm not going to go into the details because all I'm interested in is what the equatorial branch of that. But he explained in his wonderful theory, very simple, extremely simple, that the world should consist of, or the ocean should consist of gyres, okay, in which the western part is the swift flowing northward, or poleward, I should say, because of the combination of the wind stress and the beta effect and the friction. And that's why we have the Gulf Stream. It was the first explanation for why we have the Gulf Stream. But if you look at Stommel's solution, he also has an equatorial branch to his gyre. Okay? So think about the gyre that goes like this. There is a northward flowing current, Gulf Stream, say, but there is an equatorial branch. The equatorial branch, the intensity does depend on the size of the ocean. So in order to close it in each ocean, in the Pacific Ocean, you can expect twice as large transport going westward along the equatorial Pacific just because it is twice as large. If everything I'm saying is correct, then the explanation for the westward motion, the westward flux along the equator of the three oceans is the basin size wind stress and the part of the gyres that goes on between the equator and, say, 30 or 40 degrees latitude, and not the local winds right on the equator, okay? And all that is because we have a good estimate for the evaporation length, for L. If you want to buy it, fine. If not, your money back is guaranteed. Let's move on. 4 weeks ago, I could have said, in the case of the Gulf of Eilat, in 1970, up to 1979, there were lots of estimates about the evaporation. People were worried about the water balance in the Gulf of Eilat. I think I'll finish it quickly. And the estimate for the evaporation rate, I'm talking about the middle of last century, varied between 2 and 4 meters per year. Now, in my first paper ever, even before I went to grad school in physical oceanography and knew what physical oceanography, we looked at data that was collected by the late Professor Rice in the Gulf of Eilat, just analyzed it. It's myself and David Donati, some physical oceanographers might know. And we estimated the residence time of a parcel of water entering to the straits from the adjacent Red Sea all the way to the northern end and then making its way back by about 4 months. Almost every input parameter we used was incorrect. Okay? We used the wrong evaporation rates because we didn't have any others. Later on, I calculated the evaporation rate somewhat more, using more modern tools. It's about half of what people thought. But let's go back to the residence time and see what happens if we now apply the evaporation length. So we know that the evaporation length, as I showed you before, is about 26, I think it's 2 to the 7, 26, what did I say? Million meters, right? 26,000 kilometers. So what can we say about it? So if you take the modern estimate, this is 26 times 10 to the 7th, and we know Q, okay? Q is about, as I said, 1.8 meters per second, half a centimeter per day. If you plug it in there, you get a northward velocity of about 1.3 kilometers per day. Now you have to take H to be the height, half sill height, because the water coming in and coming out. Okay, sill depth is about 200 and some meters, so you take 100 meters. Again, if you know 1.3 meters per second, we know the size of the Gulf. It's about 180 kilometers. So you divide one by the other, and you get about 4 months or 120 or 140 days or so, very close to what I estimated before I knew anything about Stommel and Fofanov and all the great guys and Melvin Stern in the Gulf of Eilat. Somehow, the salinity data that we had there gave us the right answer in terms of the residence time of a water column in the Gulf of Eilat. Not a big worldwide problem, but it's an interesting going back to my first paper. One last application of the idea of evaporation length. If you look at, I think I talked to you about it. If you look at flow around Greenland, entirely different site. It has Greenland has a shape of at least the southern half of Greenland has a shape of a triangle, and ice accumulates over Greenland. It's a huge continent, island with lots of ice, and the ice melts at least part of the year. And the ice melt goes, of course, into the adjacent oceans. So you should think about the evaporation length in terms of negative evaporation, or fresh flux, flux of fresh water. So Q is just negative. And again, it's assumed that it goes the same to all points around Greenland. I'm not sure. So here's Greenland. Here's its eastern part. Here's its western part. Let's do an exercise. Again, we take soda. I mean, I've never been to Greenland. So we take soda and we take the maximum salinity and then two soda grid points on its both sides. So we average about 5 points, okay, which is about 50 kilometers, so about 250 kilometers across the maximum salinity. And if you do it on the east side and on the west side, then what happens on the eastern side, you see this is S. Remember that it's negative because the salinity is actually decreases as you go south. And what happens is that you can calculate now the evaporation length along the east and along the west side of Greenland. So if you do it, you end up with a number that's about 100,000 kilometers evaporation length again on the east side, whereas it's about 20,000 kilometers on the west side. So again, if you look at the same amount of fresh water, assuming Q is identical on both sides, this means that the transport on the east side is about 5 times that on the west side. So the question is, where does the water go? It cannot negotiate, but where does it go? It's huge amounts of water that cannot negotiate the southern tip of Greenland and move. It's a very sharp curve, and a big truck cannot, do what a motorcycle does, and negotiate the curve. So some of it is lost, but it's about 80% that's lost. And I think there is an indication to that effect in the recent paper that appeared in Nature Geoscience, I think, by a gang headed by Hugo and Annalisa Braca was on the team, in which they did numerical simulation and found similar effects. Okay, so I told you that it's about 5 times, not clear where it's going, remains an open question. Let me sum it all up and thank you all very much for your attention. And if you have questions, it took me a bit longer. So yes, Josephina. Oh, there's a gyre.
Yeah, I know it's a gyre, yeah.
So we went on the west.
But I understand in that sense the conversion from the edge, because, but I'm not sure if that I can...
Look, I wasn't on that cruise reported by Srivastava et al. In 2007. They chose to take a transit north-south along 57. I think the reason is because they felt it's the western branch of the Indian Ocean gyre. But maybe they're wrong, I don't know.
Okay. And the other comment is regarding the equatorial, but I know the form will not say where the water moves, the acceleration, of course, in terms of the book that you're mentioning, but we also have a countercurrent, right? So I know.
But that doesn't know evaporation. The undercurrent doesn't see.
Undercurrent, no, countercurrent.
Counter, oh, I'm sorry.
You have the gyres,
Right,
we
right.
have equatorial, but between the gyres and the equatorial, we have the countercurrent that goes to the east. So I'm just mentioning that. So I don't know exactly how that.
I'm not studying the equatorial current system. It's way, way, way too complicated. By the way, it goes back to John Knaus, may he rest in peace, who did this, one of the first works in the 1960s. So I'm not an expert on the equatorial current system. And I know that the Cromwell current is also involved in it. All I wanted to say is that the simple explanation of wind-driven surface current along the equator is a little bit too simplistic. And I think a better explanation is the gyral circulation. That's all I'm saying. Yes, Joe.
So your first argument is lagrangian, right? You're following a column, right? So it's a barotropic lagrangian, basically.
Of course.
Yeah, okay. But then you're applying it to transects, which aren't lagrangian, right? So you're on a boat which is moving at a velocity not with the fluid, which means that you have advective effects which could be contributing to the salinity changes. So, for example, when you're coming around Greenland, if you're going from a region, you just pick a direction and you're steaming along, you go from a saltier region into a fresher region just because of that, then you'll see a salinity fall, which may not have anything to do with evaporation, it's just because you've taken that track. Right? So wouldn't it be better to be doing this with drifters, for example, where you're measuring salinity if the drifter could do this, and then you would actually remove the advective effect. I think this is also why you're seeing such weak evaporation over the Gulf Stream, because you're in a strongly advective regime. On the right side of the Gulf Stream, there's a lot of evaporation, right? So, but because you're steaming through this in the non-Lagrangian effect, I think that may be why it's happening. I don't know. What do you think?
I think that what I do is I sample columns of water that have migrated and had undergone evaporation in my cruise. Now, obviously, when the cruise takes 2 weeks at most. In that time, the velocities are tiny. The U is tiny. It's hardly distinguishable from zero.
Yeah, if you apply this to a basin like the Mediterranean and you don't have much motion, then you think about the whole thing as a single column. Then it makes sense, right? Because then you can steam through it. But if you're in an advective regime where you have large lateral gradients in salinity and there's currents too, that will contribute to the changes.
But this is part of the game. The current is my U. The current you're talking about is exactly this U.
Well, but if you're on a transect, then the U is the speed of the boat, not the speed of the fluid parcel.
Well, boat is hardly moving in this sense. Think about 2 weeks. What's the distance it can cover?
But I think it's a similar question I was doing, because in the Indian Ocean you are doing transect like this, and a particle will go around the gyre, it will take almost a year to go around. And the transect is just in this direction, so that's what confused me. The other examples are like the average in the Mediterranean, or the Red Sea, or the Gulf Stream make more sense in the sense that you are going with the flow.
So I suggest you two talk to each other, because you think the Gulf Stream makes sense. He thinks it doesn't make sense. So why don't we all... That's what I said. I'll go have coffee. Yes, Daniel.
I had a different question, but I guess it's actually related to that. So your approach was Lagrangian, but then it heavily depends on the fluid velocity, which is frame dependent. And I guess it's somehow the question, like going on a boat, or going with the buoy, or sticking with your geographical coordinates. That somehow seems to enter the game, and so do you have? Maybe it's actually the same question, or somehow that confuses.
I think there is I think what you're expressing is a sense of uneasiness. It's so simple, it cannot be correct. It's so simple, there must be something wrong. He's fooling us. And the answer is, look, I'm looking at the column of water, remember the first slide, okay? A column of water that moves in a certain direction. I don't care why it's moving, okay? And all I'm saying is this column is undergoing net evaporation while it's at the surface. And I'm sampling it, the soda samples it for me. So I'm looking at this column, and I find it here. Then, of course, it's not the same column, but assuming homogeneity, what I found now here and here are actually columns that originated, maybe a year ago, maybe 2 years ago, who knows where. But it works. I mean, if it didn't work, we have about 10,000 explanations why it shouldn't work. But since it works, or at least it seems to be producing very sensible results, Mediterranean, go all the way, averaging, over 2,000 from Venice all the way to Tunisia, and it works. Yeah.
Do I remember well that the level of the Dead Sea is around 1.5 meters, so it has practically no inflow in the 1.5 meter per year as a reference point for evaporation?
I wouldn't know. I thought it would be. I thought it's a little higher, but not much. Why?
No, because
150, I think, is a bit low. But,
I read somewhere. So, because you mentioned that the earlier estimates.
I think it's very dry. I mean, you're between deserts. Only one.
1.5 meters per year.
I would have thought 1.75 or so, or closer to 1. Give me 10% and it will be. But we're arguing about 10%. You realize.